right, so we are here to finish the last little bit of problem 2 for doing some problem solving for the midterm coming up next week, and then to do one more problem after this. So just to remind you where we stopped in class, we had some income normally distributed with a mean of $1,100 and a standard deviation of 150. So the distribution of incomes at this company are normally distributed, so they look like a normal distribution. They look like a bell curve with a mean of about $1,100. So that'll correspond to a z-score of 0, because the z-score of 0 corresponds to the mean of the data, and a standard deviation of about 150. So if we sort of go here and I look for a height of this curve that's about 2/3 as high as the top of the curve, that's where I'll write my one standard deviation. A standard deviation of 150, so that is 150 plus 1,100, that's 1,250, and then we can go down 150 minus, that'd be 950. So that's sort of what my distribution looks like. And in class, we found the percentage of trainees that earn less than $900 a month, and we found that number to be in order to find that, we need to find the z-score of $900. So z-score of $900 using the formula for z, which is that we're going to do x minus the mean divided by the standard deviation, is 900 minus 1,100 divided by 150. And when we did that, calculator. We got that the z-score needed to be negative 1.33. So I'll do 900 minus get negative 1.33. So in order to solve this question, we need to look up on our z-table chart might be kind of small, but we're looking on the z-table chart for the value of negative 1.33, and I'll find negative 1.3, and this is probably really hard for you to see, but we followed it over here and found 0.0918. So the z-score, z equals negative 1.33 corresponds to 0.0918 on the table, which means that a z-score of negative 1.33, so $900. The area to the left of $900 is equivalent to saying the area to the left of the z-score is negative 1.33, and that was 9.18% of the data. This question specifically asked for the percentage of trainees, and it said to round answers to 2 decimal places as necessary. So I say that that's 9.18%. I'm going to skip over the first quartile because we did that one, and I'll skip down to the third one, which says that 68.26% of the incomes are between these two numbers. This is really something that looks more like a question that would occur on the third problem than the second problem, where we're looking for confidence intervals. So this question is really asking, what is the 68.26% confidence interval on our estimate of the mean? And that's what's coming up in the third problem. Something like this could occur on the second problem if the number was 68.26, because 68.26% is a number that you might recognize from the empirical rule, is one standard deviation away from the mean. Okay, so this question is saying what numbers, what dollar values are between 900 are within one standard deviation of the mean. And I've already actually written this here. So within one standard deviation of the mean is between this number and this number, which is 950 to 1250. So the empirical rule tells me that for normally distributed data, and we are normally distributed data, 68.26% of all observations fall within one standard deviation of the mean. So the answer to this is 950 up to 1250. Another thing that could show up on a question for problem 2 like this, I would only ask you for 68.26% of the data or 95.44% of the data. That's 2 standard deviations. So 2 standard deviations of the mean would be another 150 below this and another 150 above this. And 99.74%. Well, that's 3 standard deviations. Okay, so, and the last part on this is find the probability that an income is between $1,100 and $1,200. So I'll redraw my standard normal curve with a mean of 0 and a z-score of plus or minus 1 being where the curve drops down to about 2/3 of its peak value. And we are looking for, we want probability between 1,100 and 1,200. In order to use the z-table to look this up, we need to figure out the z-score of 1,100 and then figure out the z-score of 1,200 and find the area between those two numbers. So z-score of 1,100 is 1,100 minus the mean, which is also 1,100, divided by the standard deviation, and that's 0. The z-score of the mean is 0. The z-score of 1,200 is going to be 1,200 minus 1,100 divided by 150. And I got 0.67. And I'll round that to 2 decimal places, even though the question asks me for 2 decimal places in the end. So typically we'd take 3 decimal places here. I'll round it to 2 decimal places because I know that when I go look this up in the table, the z-table is only given to 2 decimal places. So the equivalent question to the probability between $1,100 and $1,200 is the question that says, what is the area under the curve of the z-curve between a z of 0 and a z of 0.67? So we're looking between 0 and about 0.67. Shade that in so we can see what that looks like. So we're looking for the area of the curve there. So the z of 0, that's the mean, that corresponds to 50% of the area. So that is 50% of the area is to the left. A z of 0.67. If you didn't already know that, you could see it, if I can make it a little bigger and actually work. A z of 0, I'm finding right here. So I find 0.00, and that's 0.5000 right there. A z of 0.67, I'll follow this down to 0.6 and over along the white line until I get to 0.67, and I see 0.7486 right there. So I'll write that down. So this is 0.7486 area to the left. Okay, so if we want to figure out the area between these two numbers, we subtract this number from this number. So 0.7486 minus 0.5, because we know that the total area to the left of 0.67, I'll shade that in with pencil here, is this whole area. But we don't want this whole area, so the shading in the pencil, that's 0.7486. The shading that is just pencil with no blue is area equals 0.5. So if we just want this stuff in the middle between them, we need to do 0.7486 minus 0.5. So the probability between 1100 and 1200 is an equivalent question to the question of probability between z equals 0 and z equals 0.67. And that equals 0.7486 minus 0.5000, which is 0.24. And that is the answer to that. So again, I will remind you that on the test, the reason that this is problem solving is so that you have the chance to get partial credit. So show me some work that looks like this, so that I can clearly follow what happened if you get to the end and you don't have the right answer. Because if it's all just a bunch of chicken scratch that's really hard for me to follow, then it's hard for me to give you extra points for doing that. Okay, so that's problem 2. The third problem will be a problem that looks like this. It's going to be a problem with confidence intervals using the z-score. So problem from chapter 8. So let me read you this question. I said, a survey revealed the amount of pocket money held by each student in a sample of students. The amount in dollars or below. Assume a population mean of 2. Round this to 2 decimal places as necessary. So we're going to use the data to find a point estimate of the mean. We'll find the 90% confidence interval, the 99.74% confidence interval. I will talk about the margin of error for the two of them. And then I have another final question which says, what if I wanted the margin of error to be a quarter? How many samples do I need to have a confidence level of 90% with a margin of error of only a quarter? So here's a sort of collection of questions that are the style of questions that will be problem 3. Problem 3 won't be this long. It won't have this many parts, but it's sort of, these are the type of questions that could be there. Okay. So the first thing that we need to do is find the point estimate of the population mean. The point estimate of the population mean. The population mean, that's the Greek one, the mu here. The point estimate is our sample mean. So we need to find a sample mean. And our best guess is that the population mean will be equal to the sample mean. So that's what the point estimate means. So I need to put all these numbers into my calculator. So I will start, and you should probably start too, and we'll see who wins. Okay, so I've got my 17 data points in my list. And if I go and I pushed stat, and then I moved over one button to the right to get calculator, and then I calculate, and I'll calculate the one variable statistics. It tells me that a point estimate for the mean is the sample mean, which is 6.1175. So X bar equals 6.1175. Okay. The question says to round to 2 decimal places as necessary. I'm still going to keep this unrounded number for some of my future calculations, but my answer to A that I'm going to put a box around so that I can so that it's easily graded and not easily mistaken for something else is that I'm going to write that the point estimate is 6.12. And what are the units? The unit here is dollars, so we'll give it a unit as well. So don't forget to make your answer clear and obvious so that I can find it. It doesn't necessarily need to have a box, but a box is helpful. And don't forget that everything here has units, so put a unit in there. We've also rounded this to 2 decimal places because that's what the question asked for. But I'm keeping track of all of the decimal places if I need it for any future calculations. Okay. So another thing that we could do is check that the z-statistic and the z-statistic here is a meaningful thing to do. So for the z-statistic, between 15 and 30 samples, we require that the data are not extremely abnormal. So they don't have to be perfectly normal, but they shouldn't be really skewed in one way or another, and they shouldn't have any extreme outliers. So we talked today in class about a way to do that to make the normal probability plot in your calculator. If you remember, you can also make a box plot with your calculator, and your calculator will identify outliers that way. So if you go into second and stat plot and go turn your plot 1 on, I want to select this thing here that looks like a box plot, which I have already selected. So I come over here and I turn on my box plot. It's going to make a box plot of list 1. And I want to do the zoom 9. That'll be the zoom to the stat for the stat plot. So I type zoom and then 9, and it makes my box plot for me. So what I'm looking for with the box plot is that I want to make sure there's no extreme outliers. And you see the box plot here hasn't identified any outliers. So there's no kind of individual points to the left and to the right here. So there's no outliers in this data. That's good. And it's okay if the data are slightly skewed, but you don't want them to be extremely skewed. I can definitely see here that the data are right skewed. Right, this tail is longer on the right-hand side than on the left-hand side. Also, the median here, that would be the median that it plots in the middle of the box, is on the left side of this main box. So both of those are indicators that the data are right skewed, but they're not right skewed in an extreme way, right? This line here isn't 3 times as long on the right-hand side as it is on the left-hand side. So we're fine calling this normally distributed data and doing the things that we need to do. If this is on the problem, if this is something that I intend for you to pay a lot of attention to, I will make it very clear in the way that I word the problem. So I will ask you, are there any outliers? Are the data normally distributed? Is the z-statistic an appropriate measure to use for this data? I will say that that's very unlikely to appear in the problem. When I design the problem, I want it to be clear and straightforward, and so that you can kind of solve it and not get messed up on step 1 and have that sort of make grading all of the other steps be something that I have to redo all of your work to figure out what you did. So I wouldn't be too concerned about that showing up on problem 3. Those sorts of questions could show up on the multiple choice though. So that's a good place to look for things, to think about on things like that. And there's a few problems on the practice test that you can look to that show you how I ask questions like that in the practice test. Okay, so do this question. So there's our point estimate. Find the 90% confidence interval for the population mean. So we are doing part B, and here's what my data look like. I'm trying to find the 90% confidence interval for the population mean, where I know that my sample mean is 6.1175, and I have been told my population mean is 2.0. So I don't need to read any numbers off of my calculator for standard deviations. I am using this as the population mean. The population mean that my calculator gives me doesn't actually include all of the data from the population. It only includes these 17 samples. So you would be incorrect to copy down the population mean data, population standard deviation data from your calculator. You want to use this population mean. So I know that X bar is 6.1175, and I know that sigma is 2.0. And I'll come over here to my equation sheet and write down the equations that are relevant for Z. So the equation that I want to look at here is this one for E, which says that E, which is the margin of error, is Z of alpha divided by 2 times sigma over the square root of n. And it's not on the equation sheet, but the confidence interval that you were looking for will have an upper limit of X bar plus the margin of error and a lower limit of our point estimate X bar minus the margin of error. So we just need to figure out what these things are. Sigma, that's 2. N is the number of samples, that's 17. I should write that down, but you can also just count up the data points. We need to figure out what Z of alpha divided by 2 is. So for a 90% confidence, alpha is 1 minus 90%, or the decimal form of 90%. So alpha is 0.10. Alpha over 2 is 0.05, 0.1 divided by 2. So we are going to look for, look up in our table and look for Z of 0.05. So we were looking for an alpha value of 0.05, which means that we are going to look for a Z-score we're going to look up Z equals not 0.05, but 0.95 in the table. So alpha values are a little bit confusing why it is the way that it is. So it might be easier to talk about just with the curve. Our 90% confidence interval is something that we want a lower limit, which is going to be X bar minus the margin of error, and an upper limit, which will be X bar plus the margin of error, such that 90% of all of the observations lie between the lower limit and the upper limit. If we've got 90% between the lower and the upper, that means that I have 5% of the data here and another 5% of the data here. Right, so in total, the 5 plus 5 equal 10% that's left. So we have an alpha value of 10, of 0.1, which that alpha value of 0.1 corresponds to a 90% confidence interval. That's what the language of alpha means. In order to find 10% of the area under this curve, we actually only want to look at one of these tails, the 0.05. Okay, so that's the procedure. So we're looking up for our alpha value of alpha over 2 of 0.05. We're going to look up Z equals 0.95 in the table, and that will be what Z of alpha over 2 is. Okay, so E is Z of 0.5, 0.05 times sigma over the square root of n. To find Z of 0.05, I'm going to look up Z of 0.95. And so I'm coming over here and I am looking for where 0.95 of the curve, and I see that there's actually these two numbers here. I see 0.9495 right here and 0.9505 right here. So the area under the curve that is 0.95 is somewhere between these two numbers, and it's actually exactly between these two numbers. So there's no one better one to pick here, so we can pick either one. So I'll pick this one. You will also get this question right if you pick this one. So I'm going to pick 0.9495, and if I follow that over, I see 1.6, and I go it up to a 4. So that is 1.64. So in my thing here, I'm going to write 1.64 times 2 divided by the square root of 16. And I got 0.82 as my margin of error. So this distance from the mean up to our upper limit of what our 90% confidence interval is 82 cents. So our upper limit is 6.1175 plus 0.82. And that is, I'll round this now to 2 decimal places because that's what the question asked for. 6.94, $6.94. And my lower limit is 6.1175 minus 0.82, and that is $5.30. So as our answer to this problem, I will write that with 90% confidence, the population mean is between $5.30 and $6.94. Okay. The next part, let's go back to our problem. Find the 90% confidence interval for the population mean. Oh, we did that one. Find the 99.74% confidence interval for the population mean. So you might recognize this 99.74 as the number for which is the 3 standard deviation number, right? 99.74% of all observations lie within 3 standard deviations of the mean. But let's say that we didn't recognize that. We can still get the right answer here going through the same procedures that we did for the 90% confidence interval. So I'm going to do the same thing that we did before, only I'm going to have area under the curve be in this tiny little bit of area under the curve. So 0.9974 minus 1 minus 0.9974. So we're looking for something that amounts to 0.0026 or 0.26% of the area under the curve. So that is my alpha value there. I'm going to divide that by 2 to get a z of alpha divided by 2, so I know what area under the curve I am looking for with my z table in order to solve the problem. So just to write this out here, I will say that 0.0013 is here. So this is 0.13% of the area. And same thing over here. So this is 0.13% of the area as well. And so we are going to go to the z table and look for, so let me write this, so 99.74% confidence interval means that alpha is 1 minus 0.9974, which is 0.0026, which means that alpha divided by 2 is 0.0026 divided by 2, which is 0.0013. Okay, so I'm going to go over to my z-table and look for the area under the curve being 0.0013, and that is the number that I will use in my margin of error formula. Oh, I said that wrong. I'm not going to actually look for 0.0013. I'm going to look for 1 minus 0.0013, which is 0.9987. Then I come over here and I find 0.9987 right at the value of z equals 3.00. So if I didn't remember that a 99.74% confidence interval was asking for me for 3 standard deviations away from the mean, I would have found it just by looking through here. So here I go and I see that z equals 3.00 for this area. For 99.87% of the area. Okay, so I said z is 3.00 if I want to find when 99.87% of the area is to the left of that value. Okay, so now I can figure out my margin of error. So my margin of error is z of alpha over 2, which we just found, right? So z of alpha over 2 is z of alpha over 2, which is 0.0013, and that equals 3.00, times sigma divided by the square root of n. So that is 3 times 2 divided by the square root of 17, and that margin of error is 1.5. So we got a bigger margin of error than we found before. And I want to check and make sure that that makes sense. Okay, so for part B, I had a margin of error of 82 cents. For part C, I have a margin of error of $1.50. And I'm going to skip ahead to part D, which one has a larger margin of error. It's definitely part C. And does that make sense? I hope that it makes sense, right? With a 99.7% confidence interval, we need to have a larger confidence interval than we would need for a 90% confidence interval. So my 90% confidence interval is going to be kind of this range here, where I'm looking between here and here, where now the area to the left of this number is 5% of the data. Whereas for my 99.74% confidence interval, the area to the left of this number is only 0.13% of the data. Okay, so as our confidence interval goes up, as we want to be more sure that that our estimates, our range of possible values, actually includes the true population mean, we're required to take a larger and larger and larger confidence interval. And there's always some push and pull between this confidence interval. There's always push and pull between precision and certainty, right? With this really high confidence interval, we are very certain that we are much more certain that we have the true population mean in our data. But we can be much less precise in this sort of a situation, right? We're going to have a range of values that's going to be almost twice as big with $1.50 compared to 82 cents because we're requiring this larger confidence interval. So there's always this push and pull between certainty. Are we certain? We are more certain with this estimate. And precision, right? How small is our margin of error? Our margin of error is smaller for a smaller confidence interval. Another way to get both certainty and precision to increase is to do part D, is to have more and more samples If you want to have both precision and certainty, you need more samples, and that's the only way to get it. So got a little bit ahead. Let's finish this problem off. So we said that the margin of error is $1.50, so our point estimate plus $1.50 is $6.12 plus $1.50. That is $7.62, and our point estimate minus $1.50 is $4.62. So with 99.74% confidence, the population mean is between $4.62 and $7.62. And that is my answer. Okay, which of the two estimates has a larger margin of error? We already talked about this, so I will go ahead and say that that is the 99.74% estimate. Find the sample size needed to have a confidence level of 90% and a margin of error of 25 cents. So with this sample size of only 17, where did I put this? It's down here. With our sample size of only 17 and a 90% confidence, we ended up with a margin of error that gave us a range between 530 and 694. So our margin of error was 82 cents. So now this question is saying, well, how big does N need to be in order to turn this from 82 cents down to a quarter? So this number here is going to be the same. This is the same. This is the only number that is going to get bigger. So we want 25 cents to equal 1.64 times 2 divided by the square root of N. And we need to solve for the square root of N. So that's the procedure. And if I come over here to the equation sheet that I'll have for the test, I see that there are two formulas here. One is the margin of error, and one is that same formula as the margin of error formula, only it's been solved for N. So you don't need to solve it for N. I've done it for you. And I'll go ahead and write that formula down. It says that N equals Z of alpha divided by 2 times sigma divided by the margin of error that I want squared. And I'm going to copy down the same numbers that I had before. So I was using 1.64 was the Z of Z was Z's Z of 0.05 times 2 standard deviation. And now the margin of error that I want to achieve is 25 cents. I'll square that, and I get 172.1 samples. This is a quite non-physical number. You can't have a not whole number of samples. You always round this up to the next number. Even though this would round down to 172, we're going to round it up to 173 because we actually, 172 will give us a margin of error too big. So we always want to kind of aim on the side of getting more samples instead of fewer samples. So we'll round this up. And we'll say that N equals 173 samples.